Okay, this is Chapter 2, Section 6, the rational root theorem. This is our last section of Chapter 2. And so the objective here is to find all zeros of a function using the rational root theorem. So all zeros means real and imaginary. And a little thing here is mind your P's and Q's. You'll see exactly what that means shortly. So the rational root theorem is a method that helps us find all possible roots of a polynomial equation. Like I said, real and imaginary roots. And so part 1, finding just the possible real roots. So possible, they may not be all of them, but possible. The method would be to have your equation in standard form. So from the highest exponent to the lowest. When it's set up like this, you'll notice that this value here is going to be P. And P's, values for P are any factors of 8. So anything that divides evenly into 8. So 1, 2, 4, and 8. Now those could be positive or negative values. So I'm going to go ahead and put plus or minus in front of each of those. Okay, next, the leading coefficient, which is this value here next to the leading term, is going to be the Q. So these are your P's and Q's. We'll do the same thing. So factors of 2 are numbers that divide evenly into 2, which is just plus or minus 1, plus or minus 2. Next, to find the possible roots, we'll take P divided by Q. So we'll divide each of the P's by a Q. So 1 divided by 1 is 1. 1 divided by 2 is half. So then 2 divided by 1 is 2. 2 divided by 2 is 1, which we already have 1 here, so we don't need to write it again. Then we have 4 divided by 1 is 4. 4 divided by 2 is 2, which we already have a 2, so we're not going to write that again. Then we have 8 divided by 1 is 8. And 8 divided by 2, which is 4, and we're not going to write that 4 again. So this is all we have for possible roots. So again, these are the possible roots. And that just means that these could possibly be the roots, and so there's no other numbers that will make up the roots, but also that doesn't mean they're all the roots. Meaning it may be 1, half, and 2, but not 4 and 8. So these are all the possibles, but they may not all be necessary. Okay, so example 1. Find just the possible real roots of the following polynomial. So we're going to do the same thing, but like I said, it needs to be in the standard form. So from the highest exponent to the lowest, so we need to rewrite this one. So we'll have to minus the 9x and add this 2, so that it'll be equal to 0. And then we'll continue the same way. This coefficient here, or the constant, is our p-value. Then we need to find the factors of 2, so numbers that divide evenly. So that's just plus or minus 1, plus or minus 2. Then this value here, the coefficient in front of our leading term, is 3, and that's going to be our Q. And factors of 3 are plus or minus 1 and plus or minus 3. So again, to find our possible roots, we'll do P divided by Q. This just means 1 divided by 1 is 1. 1 divided by 3 is 1/3. 2 divided by 1 is 2. And 2 divided by 3 is 2/3. Okay, so these are all of our possible real roots. Not the actual roots, but possible roots. So we're going to skip example 2 and go to this example here. Find all of the roots of the following polynomial. So you see it doesn't say possible, but it says all of the roots. But the first step here is to find, use our P's and Q's to find the possibles. So it's in standard form. We can see that the 9 would be our P. And factors of 9 are plus or minus 1, plus or minus 3, and plus or minus 9. This, in front of the x is implied 1 because 1 times anything we know is that number. So if you need to, you can put the 1 there, but this is our Q. 1 is our Q. So Q, the only factors of 1 are 1. Then we'll do our P over Q as usual to find our possibles. P, 1 divided by 1 is 1. 3 divided by 1 is plus or minus 3. And 9 divided by 1 is plus or minus 9. So now given these possible roots, we need to see which one of these actually are roots of this polynomial. So to test to see if positive 1 is a root of this polynomial, we can use synthetic division. So if I go ahead and write 1 here, notice we will need some placeholders because we're missing x to the third and the x. So first we have 1, 0, negative 10, 0, and 9. Bringing down our 1 times 1 is 1, adding this, 1. 1 times 1 is 1. This is adding, we get negative 9. Negative 9 times 1 is negative 9. Adding, we get negative 9. Negative 9 times 1 is negative 9, and we get 0. So that tells us, because we got a remainder of 0, that 1 is a root. Next, we have to see if 1 is a double root by repeating the process with our new coefficients. So 1, 1, negative 9, negative 9. If we get a remainder of 0 again, then we know it is a double root. 1, then 1 times 1 is 1. Adding 1s, we get 2. 2 times 1 is 2. Adding these, we get negative 7. Negative 7 times 1 is negative 7. Adding these is a negative 16. So that means that 1 is not a double root. So we don't have to worry about this. Okay, so we're going to move along and see if negative 1 is a root of this polynomial. So instead of using the original coefficients that we did here, we can now use these values because we found that it's a remainder of 0. So let me make some more room. We're going to test negative 1 and use these values now. So 1, 1, negative 9, and negative 9. Bring down our 1. 1 times negative 1 is a negative 1. Add these together, we get 0. Times negative 1 is 0. Add these, we get negative 9. Negative 9 times negative 1 is a positive 9. So again, we get 0. So now we know that 1 is a factor of our original polynomial and negative 1 is a factor, or a root. Now notice our original equation was x to the fourth. And when we found that 1 was a factor, we came up with this quotient, which means this first value would have been x to the third. Then we tested the negative 1, and our new quotient would have started with an x squared. Once you get down to an x squared, we can't use synthetic division anymore. So let's go ahead and write what we have. So if 1 is a root, that means we have x minus 1 is a factor. This negative 1 is a root, so that means x plus 1 is a factor. Then write what we have left here. So this is x squared minus 9. So then the way that we've always found the roots is by setting them equal to 0. So like we said before, because we use the synthetic division, we know that x is equal to 1, x is equal to negative 1, and if we set this equal to 0, we have x squared equal to 9. We take the square root of both sides, and you'll find that x is equal to positive or negative 3. So that is two real roots there, 3, 4. So that's exactly what we should have got. X to the 4th means there's 4 roots. Okay, so just to review, when you're finding the roots and you're given an equation, write down your p's, your q's, then take p divided by q. Then you'll use synthetic division to test if they're a root. And of course, if you get a 0, a remainder of 0, that means it is a root. And then continue checking each one using the new coefficients. When you get down to an x squared, you can't reduce anymore. So then you can either factor or use the quadratic formula once you get here. And then that's how you get all your roots. Okay, so that's all for this section. I'll see you all tomorrow. Hope you have a great night.